Hi students, welcome to the next topic from magnetic effect of current. Last class we have discussed about Biot-Savart's law and its application also. So today class is also the continuation of application of Biot-Savart's law, but there is slightly something interesting will be here. Okay, because there are a lot of tricky questions can be formed from today's sessions. So listen very carefully. So we'll move to the topics without wasting the time. Okay, so you can write out the heading magnetic field. You have to write on the heading magnetic field. Magnetic field due to a magnetic field due to who is producing the magnetic field. Magnetic field due to a straight current carrying conductor, magnetic field due to an infinite current carrying conductor, already we have seen. So here magnetic field due to a circular current carrying conductor, circular current carrying conductor, circular current carrying conductor. Magnetic field due to a circular current carrying conductor. This is the topic for today. And we'll see a lot of sums or numericals from these sessions. Okay, so we'll start with the first concepts will be here. So we have a circle, listen very carefully, and we are going to find out magnetic field at the center. And the circle is carrying a current I is flowing like this in a circular fashion. And we are going to calculate the magnetic field at the center of the circular current carrying conductor. So where we are calculating the magnetic field? We are calculating the magnetic field at the center of the conductor. This is a conductor, right? At the center of the conductor, we are calculating the magnetic field. So this current carrying conductor is carrying certain amount of current also. So how to do this one? Here we can apply Biot-Savart's law. So what is Biot-Savart's law? States that B is equal to mu 0 by 4 pi, magnitude format I am writing, I dl sine theta divided by r square is the equations for magnetic field. Next step. Okay, first we'll see the direction of the magnetic field. See, thumb is pointing the direction of current. If you look, will be here, your thumb is pointing to the direction of current. So your other curling fingers, these four fingers representing the direction of magnetic field. So your thumb is pointing in the direction, so means thumb is in this direction. So my fingers within the circle is going into the board and there it is out of the board. So with respect to this point at the center, my fingers are going inside. My fingers are going inside. So the magnetic field is inside with respect to this current. Now if you look, will be here on the bottom side also. My thumb is coming towards me. So if I holding the conductor like this, my other fingers are going inside. So magnetic fields are inside. So direction is very clear. Magnetic fields are inside. In your case, you can say into the paper. Okay, now I dl sine theta into r square. What is sine theta? Theta is the angle between, while we are discussing about current carrying conductors, we told this element is called dl and this is called r and this is called theta. So theta is the angle between dl and r. So now if I am taking a small current element of length called dl, the ideal means ideal together. Okay, while we are writing the vector format, I told mu 0 by 4 pi into I into dl cross r divided by r cube. So dl cross r is the vector format and dl direction, its a length direction is same as I direction. So this is called I dl together. And this is called my r. R is the distance towards the center where I am going to calculate the magnetic field. In this Biot-Savart's example, we are calculating the magnetic field here. This is at a distance of r from here. So this is ideal. And what is the angle between them? Is 90 degree. Okay. So dl is giving a small magnetic field. So normally we are writing as dB because it is dl, small current element. So this will be written as dB. Now we'll check these points out. We'll substitute in dB is equal to mu 0 by 4 pi I into dl into sine of 90 divided by r square, because I know angle between ideal and r. Okay, so within bracket I can write angle between ideal and r. Ideal and r. Actually, it is between dl and r. Why we call it as ideal means I is giving the direction for dl. That's what we together is called ideal. Vector form is like this. Okay. So now once we simplified, what is sine 90? It's 1. So mu 0 by 4 pi into I dl divided by r square. This is called dB. So dB is the magnetic field due to this small current element. But my circle is not this small piece. My circle is composed of, or is made up of many number of small pieces. So to find out the total magnetic field, I have to integrate both on the LHS and RHS. So now I'll integrate. Integral dB. Integral dB, you know, it is nothing but is called B. What all things will be constant? Mu 0 by 4 pi into r square. So mu 0 by 4 pi is constant. 1 by r square is constant. Integral dl. Integral dl for a circle. For a circle, if I am integral dl is nothing but L. L for a circle is how much? 2 pi r, perimeter. Perimeter of the circle. This is the maths basics, nothing else. Perimeter. Integral dl is called L. L is equal to 2 pi r, which is called perimeter of the circle. So I am substituting this relations will be here. So mu 0 by 4 pi into 1 by r square into 2 pi r. R cancel, pi cancel, 2 cancel, 4 cancel. So what will come? Mu 0 by 2 into pi got cancels. Here how much will be there? 2 will be there and 2r will be there. Okay. So mu 0 divided by pi cancels, 2 4 cancel, balance is 2, and here one balance is r. So 2r. So magnetic field due to a circular current carrying conductor is mu 0 divided by 2r. R is the radius of the circular current carrying conductor. This relation is very important, both for JE mains in case if you are going to write, and as well as for Neet in case if you are going to write. So for all the entrance examinations, whatever you are going to appear, this is important. Mu 0 by, mu 0 I is missed, right? This is I. So mu 0 I divided by, mu 0 I missed will be here. So this is not 1, I by. So mu 0 I divided by 2r. Mu 0 I divided by 2r is the equation. Some reference textbook you can see mu 0 by 2a. Some textbook will be using a letter called small letter a. A is nothing but radius. Here r is nothing but radius. So letters are not significant, but the concept is important. Mu 0 I divided by 2r. So hope this is clear to you. Magnetic field due to a circular current carrying conductor at the center of the circle. So here this B is nothing but this B. Both are same. Okay. So let's move to the next subtopic. Okay, this is a fundamental of this one. Nothing else will be here. Okay. Now we'll do some analysis on top will be here. Suppose I have two conductors like this. One conductor is a circular half circle conductor I. Another one is I have a quarter circle conductor like this. Both are carrying a current I, both are carrying a current. What is the magnetic field will be here? What is the magnetic field will be here? In this case also, we can apply from here, all things are constant. B is equal to mu 0 divided by 4 pi. Pen is not clear, I guess. Let me take another color. So fine. 1 second. Okay. So B is equal to mu 0 by 4 pi into I by r square into integral dl. What is this integral dl will be here? 4 pi I by r square. Full circle is 2 pi r. Okay, full circle it is 2 pi r. So this is half circle. Half circle means what? Half of full circle. So it is 2 pi r by 2. Okay, 2 pi r is full circle. So this the whole term is representing an half circle. Half circle, right? Full circle by 2 is called half circle. So we'll simplify this one. So what we will get? Mu 0. Here pi cancel, 2 cancel, 2 cancels. So mu 0 I divided by 4r. See, half of this one. For full circle mu 0 by I by 2r, and for half circle mu 0 I by 4 pi r. Correct half. Now if you look for quarter circle, mu 0 I divided by 4 pi r square. What is the integral dl in this case will come? It is 1 by 4th of the circle. So which means 2 pi r divided by 1 by 4th means here by 2 for half circle. For 1 quarter, for 1 by 4th of the circle. If you connect 4 pieces like this, 1 piece, second piece, third piece, 4 piece, you will get full circle. So it is 1 by 4th of this one. So what will come? Mu 0 I divided by 8r will come. Magnetic field. So magnetic field due to a, this is I can say a quarter circle. Magnetic field due to a quarter circle. Magnetic field due to a half circle. Magnetic field due to a half circle. Magnetic field due to a quarter circle. Mu 0 I by 4 pi r, mu 0 I by 8 r. These are the main things which are exist. Okay, mu 0 I by 4 pi r and mu 0 I divided by 8 r. Now if in case this is clear and for full circle it is clear, mu 0 I by 2 r, mu 0 I by 4 pi r, mu 0 I by 8 r. In case the third one, if a arc is given of length theta degree. Okay, if an arc is given like a theta degree, so how I can find out? I can written as a general formula, mu 0 I divided by 4r is for the full circle, sorry, 2r is for the full circle. So I can say theta divided by 2 pi. Theta divided by 2 pi, or I can written as or I can written as, this is for angle in radian, this is for angle in radian, or I can written as B is equal to mu 0 I divided by 2r into theta divided by 360 degree. This is angle in degree, this is angle in radian, this is in degree, angle in degree. Okay, so let me take an example over here. See, this is an arc and which is carrying a current of I, and I am going to find out the magnetic field at the point here at the vertex. Suppose then if theta will be depends upon the value of theta, we can apply any formula. Okay, so now in case of an half circle, for a full circle it is 2 pi. For a half circle, how much is the radian value? It is called pi degree for a half circle. So it is pi means pi will get cancelled. You will get mu 0 by 4r. This equation if you get. For a quarter circle, for a full circle this is 180 degree. For a quarter circle this is 90 degree. So if you put a 90, corresponding to 90 is what? Pi by 2. Pi by 2, if you substitute, it will be here, pi and pi get cancelled, that 2 will come to denominator, so it here become 4, and mu 0 I by 8r will come for you. So in case of a degree also you can place it like this one. If theta equal to 90 degree, you can place in 90. 90 by 360 means 1 by 4. 1 by 4 into 2 is 1 by 8. So mu 0 I by 8r. In case of half circle it is 180 degree. 180 by 360 is 1 by 2. 1 by 2 into 2 is 4r. So mu 0 I by 4r. You will get this relation also. So what I have tried to convey is, for a full circle the magnetic field intensity is mu 0 I by 2ir. For a half circle mu 0 I by 4r, and for a quarter circle mu 0 I by 8r. For any circle with a certain value is given, theta value is given, theta maybe it is given to you in terms of degree, you can use this equation. If theta value is given to you in terms of radian, you can use this sorry, you can use this relation. So both of this will give rise to a same results. Okay, this is the magnetic field due to a current carrying conductor. Okay, this is important. Okay, there are questions will be there, you can expect some questions from this area as well. Okay, fine. Fine. Next we'll see some questions over here, and let me try to answer some of the questions to make the concept is clear. Okay, so let me move to one sample question, one example question. Suppose like this. Okay, I and I. Question is will be here, a current carrying arc is given like this one. Okay, question is simple, what is the value of B, magnetic field? At this point, of course the point is marked, we need to find out the magnetic field at the point B or at this center point. How we can calculate it? For such kind of question, you have to see how many wires are connected. Okay, I can say like 3 wires are connected. One is this straight wire which is given number 1, another one is this bigger one number 2. Oops, color. 1 second, some pen leak I guess, I just filled the ink. Okay, so above one is 2 and the below one is 3, this is 3 and this is given as 4. Okay, so let me see. So there are 4 things will be there, 4 current carrying conductors will be there, number 1, number 2, number 3 and number 4. Okay, now we'll see what are the things which are going to happen. So here we are going to find out the magnetic field intensity. Okay, so the current is in this direction and we are going to find out the magnetic field. See, we have learned one equation. See, if a current carrying conductor is like this, if you are finding the magnetic field at the center like this, so this angle is called phi 1 and this angle is called phi 2, then we have an equations mu 0 I divided by 4 pi, if this value is r, 4 pi r into sine of phi 1 plus sine of phi 2. This already we have learned. Now see, if you have a conductor and I am going to find out magnetic field along the line of the conductor, we already discussed this one. See, this is called I and this is called dl, and you are calculating the r is from the center of dl, this is called dr. So IDL and R are in the same direction. So if you apply Biot-Savart's law, dB equal to mu 0 by 4 pi into IDL sin theta divided by R square. What is called sin theta? Sin theta is the angle between IDL. So the IDL is in this direction, IDL, and R is the distance measuring from here, that is also in the same direction. See, R is also in the same direction of IDL. IDL in the direction. IDL and R are in the same direction. If it is in the same direction, the value of theta equal to 0 degree, the magnetic field is also equal to 0 degree. This is a concept we have learned. Same thing is apply for number 1. So the magnetic field due to 1 is equal to 0. Why? Why it is equal to 0? Because R is the distance from the center. R line is like this. So this is an ideal. So which means R line, and this is R line, and this is called ideal line. Both are in the same direction. See, magnetic field is a point along the direction of ideal. So magnetic field is equal to 0. Same way you can write it as B3 is also equal to 0, because see, ideal and R are in the same direction. So R is a distance from here. That is same, right? Simply we have taken as R. So that direction is also in the direction of ideal. So ideal means this is I direction. So ideal is also in the same direction. So both are 0. Next, we have to given two radius. The inner radius is R1. This is as a part of the given in the question, and outer radius is R2. Now we will find what is the magnetic field due to second one, B2. This is an half circle. So of course we know the general formula for half circle is mu 0 I divided by 4R. So in our case it is mu 0 divided by, we are going to find out B2 like this. What is the radius of this one? 4 times of R2. Direction is important. See, the current is going like this. So magnetic. So if you hold your thumb in the direction of current, so here the magnetic fields are inside and here it is outside. Within the center, my curling fingers are going into the board. So the magnetic field is inside. Direction is important. Always you have to be bothered about direction. If magnitude is 0, you can remove it. Next, magnetic field due to 4, the fourth conductor, the small one, inside one. What is the value of this one? Mu 0 I divided by 4R is a general equations. We are substituting the value mu 0 I divided by 4 times of R1. Here we have to see I is in this direction. So top side, upper side, top side, the magnetic fields are going inside, and in the bottom side my fingers are coming out. So the magnetic fields are outside. So we have two magnetic field, inside and outside. Which one is higher? R1 or R2 will be higher, will be here. I can say R2 is higher than R1. In that cases, I can say B4 is greater than B2, right? Volta, because it's in the day. R2 is higher means B2 is lesser. R1 is lesser means B4 is higher. Okay. So the total magnetic field, B net magnetic field is what? B4 minus B2 you have to calculate. So highest is B4, lowest is B2. So what is the direction of B4? Outside. So higher at outside, lower at inside. So highest minus lowest. So the total magnetic field direction is what? The direction of the highest one. Highest one means out. So we have to simplify this. B4 minus B1. So mu 0 I by 4 is constant, 1 by R1 minus 1 by R2. This is the magnetic field due to this current carrying conductor. So you can see the beauty of this one, right? How many conductors we have considered? Totally 4 conductors we have considered. 4 in the sense 1, 2, 3, 4. Every small piece matters will be here. Every small current carrying conductor can able to produce magnetic field. So 1 is important, 2 is important, 3 is important, and 4 is important. But luckily 1 and 3 is in the same line of R, because R is a distance from here. Here. But here if once you take, things will be in the same direction, ideal and R in the same direction. So magnetic field to 1 and 3 is 0. 2 and 4 is we calculated, 2 and 4 equations we have written. But the interesting thing here, it is like the direction of magnetic field in case of 2 and in case of 4 is different. If both are different, then what will happen? We have to subtract from highest value minus lowest value. B4 is highest, outside magnetic field is highest. So highest minus lowest, of course we will get a, suppose highest means you can consider like a number 10. Lowest means you can consider like number 2. So 10 minus 2, it's a positive number. So the highest sign, what is the highest sign? Positive 10. Similarly here highest sign is out. So total is outside. So outside magnetic field is given by mu 0 I by 4 into 1 by R1 minus 1 by R2. So this is a magnetic field due to this coil. Okay, hope this concept is clear to you. So I have here next questions for you in the board. I just clean up the board and take some water. So okay, so 1 by R1 minus 1 by R2. So this is a magnetic field due to this coil. Okay, hope this concept is clear to you. So I have here next questions for you in the board. I just clean up the board and take some water. So, okay, so 1 by R1 minus 1 by R2. So this is a magnetic field due to this coil. Okay, so We need to find out again the magnetic field at the point P. This is the second question in this topic. So we need to find out what is the value of magnetic field at the point B. So the point B will be here. Okay. Now I want to get your attention will be here. This we will answer it together. Okay. How many conductors will be here? 1, 2, 3. Totally 3 conductors will be there. This is conductor number 1 and this is conductor number 2 and this is conductor number 3. So totally 3 conductors will be here. We need to find out the magnetic field due to these conductors. That is the aim will be here. See, this is called infinity, an infinity conductor. Last class we have seen like for a conductor, the magnetic field at this point, if it is a finite conductor, then this is called a phi 1, then this is called a phi 2. Magnetic field B equal to mu 0 I divided by 4 pi r into, if r is the distance, then sine phi 1 plus sine of phi 2. And in case we have also seen, if this is an infinite conductor, the conductor is infinite, and if I am going to find out the magnetic field at one side, then this is approximately like this and another conductor is like this. So we have 2 options will be here. Okay. So the one of the value will be equal to sine. Here you can see if you are going to find out magnetic field will be here, then this phi 1 is approximately equal to 0 and phi 2 is approximately equal to 90 degree because it's going to infinity. Okay, in that case what is the value will come? Mu 0 I divided by 4 pi r into sine phi 1 is 0. So sine 0 plus sine of 90. So we will get mu 0 I divided by 4 pi r, we will get it. Okay. So this what we have seen for a infinite conductor at any edge. So infinite conductor at any edge, whether it's lower edge also or upper edge also. If it is upper edge, phi 1 equal to 0, phi 2 is equal to 90. If it is lower edge, phi 2 is equal to 0 and phi 1 equal to 90. So now this is an infinite conductor, magnetic field will be here. So there are 3 magnetic fields. The first magnetic field is B1 equal to, I know it's an infinite conductor at one edge. What is the value of this one? So this distance is called r. So here the distance both are given as r. So B1 will be equal to mu 0 I divided by 4 pi r. We have to immediately mark the direction also. So this is the direction of the current. So right side is a magnetic field. Your curling fingers are going inside. Left side it is coming out. So magnetic fields are inside. Okay, inside. Normally we are representing using a symbol like this. This is for inside, cross mark. Okay. Now this is a half circle. Half circle already we know the formula. So B2, what is the magnetic field will be here? So thumb is pointing in this direction. So magnetic fields are inside. So B2 will be equal to, for an half circle, mu 0 I divided by 4r, and this is also inside. Okay. And the last one is magnetic field due to a straight current carrying conductor. Here you can see I dl together in this direction and r is starting from here and toward this. So both are in the same direction. If both are in the same direction, then what is the magnetic field will be equal to 0. So total magnetic field will is the sum of these 3. Okay. So now we have to calculate the total magnet. Both are inside means you can directly add. Total magnetic field B net will be equal to, you can add. What are the terms will be common? Mu 0 I divided by 4r is common. 1 plus 1 by pi. This is the answer for the question. Mu 0 I divided by 4r into 1 plus 1 divided by 5. Both are inside. Inside means you can directly add. If one is inside, one is outside means you have to subtract highest minus lowest. Here both are inside. So the answer to the question is mu 0 I divided by 4r into 1 plus 1 by pi. Hope this is clear to you. Okay. So let me see another example question. So this is a combination of actually a wire with a semicircle. Okay. So the previous question is purely with a wire and small wire, small two wires and two half circles. Here we have one half circles, one infinite semicircles, and infinite wire. Then we have a small piece of wire, B3 line. Okay, so that is clear perfectly. Okay, now we'll see the next question. Fine. So we have a Cartesian coordinates axis. This is y and this is x and this is z. Okay. Now this is the concepts will be here. Okay, going to infinity and going to infinity. Okay, let me make it more symmetrical with respect to this. This is going to infinity. Okay, infinite, and this is a positive z axis. So what is the value of B at the origin? What is the value of the magnetic field at the origin? Origin is this point. Here I need to find out the value of the magnetic field. See, x and y axis will be given, so it is a Cartesian coordinate system. How many wires will be here? First of all, 3 pieces will be here. Number 1 this one, number 2 this one, and number 3 this one. 1 and 3 will be same, right? It's an infinite current carrying conductors. So let me see will be here what are the things are happening here and how we can able to answer it in a perfect way. See, 1 is the infinite current carrying conductor and which is passing the current outside. So you have to see will be here. You have to imagine something will be over here. So what is your imagination is like? Listen to me very carefully. You can see this is my y axis and this is my x axis. Now what will happen means, one side the current, one wire, infinite wire is coming current here. It take a turn, then it is going out. So here the current is coming inside. This point I am talking about. So current is coming inside. You can assume it's a straight wire. Current is coming inside. So with respect to origin, I know it's an infinite current carrying conductor at one edge, and this distance maybe we can mark it as r. At one edge we are going to find out the magnetic field, but direction is important. See, current is coming straight away into me. So if I hold it like this one, my fingers are going at what side? It is downside. Downside means what? Minus j. Upper, top, plus j. Downside is minus j. So magnetic field due to conductor number 3 I am saying. Okay, here, okay. 1 second. This is coming inside and taking rotation going outside. So magnetic field due to 1, as I told before, this is a conductor structure and a current is coming. Okay, you can assume with this figure current is coming inside. So current is coming inside. Listen very carefully. I will repeat it once again. My 1 and 3 got changed. This is 1, this is 2 and this is 3. So this is a y axis. So here the current carrying conductor is coming in the left side. So current carrying conductor is coming left side means it's coming towards me. So if I hold my fingers, the other side my fingers are going inside, and with respect to the origin point it is coming outside. Correct? If a current carrying conductor is coming, I'll hold my fingers like this, so it is outside at the origin point. So magnetic field due to 1 for an infinite current carrying conductor formula already I have written just before, 4 pi r, and this is in what direction? Upside. So magnetic field to a current carrying conductor, current is coming like this one. I will hold my thumb so I can see right side my fingers are going inside, left side my fingers are coming top means plus j direction. So this is in the positive j direction, this is in the plus j direction. And second one is B2. B2 is the magnetic field due to a current carrying conductor for a half circle. So it is mu 0 I divided by 4R. What is the direction of this one? You can see this is the one and the current is moving like this from red to black. If current is moving like this one, red to black means I will hold my fingers. So it's coming towards you. Correct? Here I will hold. Here I will hold means I will take it upward. So with respect to the left side. Okay. So there are two things will be there. So this is the current wire. So the wire is located like this one. So I will hold my fingers. So with respect to this point, this is going outside. Outside means towards you. If I hold my fingers like this one, right? Outside, towards you. U means, towards you means what direction? Positive Z direction. So this is positive K. Next one is B3. B3 is the current is now came here and take a rotation here, then going outside. If a current is going outside, I will hold my fingers will be like this one. So left side it is down and the origin side, when comes to origin side, it's going to top. Top means what axis? Plus J axis. So mu 0 by 4 pi R into plus J axis. Okay, here also it is coming outside, and once the current is going outside, it is going upside. So plus J axis. So J and J can be added. So we have two vectors. So B1 and B3 together, we can straight away add B1 plus B3 we can add. So mu 0 I by mu 0 I divided by 2 pi R, both are pointing in the plus J direction, and then we have a B3 will be there, mu 0 I divided by 4R, then that is in the plus K direction. So there are two components will be there. One is in the J direction, another one is in the K directions. Two vectors are in the same. So how we will find the resultant of two vectors? A square plus B square plus 2AB cos theta. So here theta is what? 90 degree. So cos 90 is how much? 0. So root of A square plus B square will come. One is this B1 plus B3. So which means mu 0 I by 2 pi R the whole square plus. Second one is this one, mu 0 I by 4 R the whole square. Two things. We have to simplify this first. Okay. So let me take this space extra will be here to simplify this. So the resultant magnetic field. So BR, I can say BR, resultant magnetic field BR will be equal to mu 0 I square constant, 2 square 4 square constant. So I can take mu 0 I constant, take it outside, 2 okay, here 2 take it outside and R take it outside. So what is comes in the bracket? 1 by pi square plus mu 0 I by R come outside. So what is will be there in the balance? 1 by 2. 1 by 2 the square is 1 by 4. So this is the magnetic field due to a current carrying conductor in this format. Hope this is also clear to you. So depends upon the question. Always the formula, you may have to use an infinite current carrying conductor, you may have to use a semicircle, you may have to use a quarter circle, anything you have to use. But the ultimate aim is first you have to derive the formula. If it is infinite current carrying conductor, this is a formula. If it is a semicircle, this is a formula. Quarter circle means I already told the formula. Full circle means I already told the formula. So once you write the formula, the trickiness is exists while finding the direction. So to find the direction, it's very simple. Thumb is pointing the direction of the current. Other fingers, with respect to that point, you have to analyze whether it is going inside, whether it is going outside. In your case, while you are writing on notebook or in a paper, it may either go into the paper or it may go to out of the paper. So depends upon that, you have to analyze it. If it is a different inside outside combinations are coming, you have to subtract it. If it is inside combination, directly of course you can add it. That's a very basic fundamental rule in vector. If vectors are in the same direction, you can add it. Opposite direction, of course, you have to subtract highest minus lowest and you have to find the directions. Hope the session is clear to you. Circular current carrying conductor. This is very important for both for Neet and JE examinations. Okay. So all the best. We'll see on with the next topics in the next class.